Hi everyone, my name is Jasper and I'm a PhD candidate at the University of Washington. In this talk, I'll be presenting Imprimer, computational notebooks for CNC milling. This is joint work, no pun intended, with my collaborators Gabrielle Benabdallah and Nadya. As machines like 3D printers and CNC mills become more accessible to non-experts, we've seen increasingly exploratory use cases emerge in science, art, and engineering. For example, 3D printing batteries on the micron scale, using cellular automata to make pottery, or using machine learning to test and design 3D printed lattices for withstanding impacts. We have solid infrastructure for common fabrication tasks. Typically, we'd have a CAD editor for producing geometry, a separate application for translating geometry into machine instructions, perhaps some post-processing after that, and then another application for deploying instructions to the machine. However, if we need to deviate from these steps to make something that established software doesn't support, we're pretty much on our own. Say we want to replicate this exploratory workflow called wireprint by Mueller and colleagues, where they print a wireframe of a model rather than the entire object. The concept is straightforward enough, but the details are not at all. There are a ton of physics involved in getting the triangles to stand up at all. And the only tool we have for this, fundamentally, is raw machine instructions, here G-code. And we really need to be able to do some testing before we can develop formalizations, just so we can get an idea of the design space. Taking a step back, we really ought to think about how we're approaching exploratory fabrication. In an article about the benefits of combining human-computer interaction and programming languages research, Chasins et al. Say that while both GUIs and languages make it easy to say common things, a language empowers users to say uncommon things too. We're interested in uncommon tasks by definition, so we should consider how to view exploratory fabrication from a programming language lens. We can see that G-code's low-level control alone is not enough. Namely, writing snippets of G-code lacks many features of programming languages that we take for granted. For example, functions, visualization, testing, previewing in situ, interoperating with outside libraries, and adapting to different machines. One promising first step in this direction is p5.fab, which provides a JavaScript wrapper around common G-code commands for 3D printing. But we need to take this idea even further than G-code as a foundation. One path forward is literate programming, where programs comprise natural language, illustrations, and interactive elements interleaved with source code. Computational notebooks, an example of literate programming, are commonly used in scientific computing, machine learning, and related fields which deal with digital data. But could we extend notebooks to the physical world as well? To test this concept, we built Imprimer, where the end user works from a computational notebook on the left to use a CNC mill with an AR projection guide on the right. In our implementation, we use the Observable notebook tool and a large CNC mill for wood called a Shopbot, whose cutting space measures 2.4 by 1.5 meters, or, in the Shopbot's native units, 96 by 60 inches. In particular, we chose to build Imprimer for CNC milling rather than for other types of digital fabrication. This is because of the steep learning curve it presents to those without prior experience, which make it difficult to break from conventional fabrication. 3 challenges in particular are choosing an end mill that's right for a given job, needing to strategically translate geometric features into toolpath operations, and understanding safety risks that can result from even minor missteps. Here, an end mill broke in half due to using too fast of a milling feed. We'll walk through the system by going through an example where fabricators can do surface milling by sampling 2D functions from math. For example, here we have the sink function, which looks like a ripple in a pond, and the user can rewrite code and change parameters to get a desired toolpath. They can then cut scale examples and experiment and deploy directly from the notebook without ever having had to do any 3D modeling. In the notebook itself, we introduce a library to help users reason about the different challenges mentioned before. They can preview, test, and iterate quickly just by editing code in a single notebook rather than working across multiple programs. There are too many details to mention here, so please check out the paper for more information. To support the library, we developed a network architecture to connect the Shopbot with the user's notebook, as well as an augmented reality overlay for visualizing movements on the Shopbot's physical bed. Code executed in the notebook directly affects both the Shopbot and the overlay. This eliminates the need to export and import files from separate programs, which is normally required. In this example notebook, we use a precondition check to ensure certain criteria are satisfied in the notebook before the user can start the Shopbot. Once these are satisfied, we can build directly from the notebook, here using purple insulation foam. In the end, we explored a range of different functions and different parameters and cast the molds on the left with plaster to get some cool math-inspired titles on the right, which would make a great decoration for a makerspace or math classroom near you. Here's a second example where we use the machine as a low-fidelity sketching interface. On the left, we have an element where the programmer can directly sketch, and the path they create is data that's stored in a variable. Because observable notebooks are live programming environments, the new data then propagates immediately to all other cells in the notebook. In this example, the updated path generates a different visualization of the machine's toolpath. The notebook also sends visualizations to the AR overlay so toolpaths can be visualized in situ. As an example of this, in the notebook, we dispatch a job to cut the C and chi. The projection shows where the mill is going to move. We notice that the finish left by the C and the H is not what we want. To change this, we simply go into the notebook and change the code cell that generates the feed rate or how fast the mill moves. We add a correction factor to slow down the feed, and then we use this new feed to cut the I and chi. This results in a better finish. And in one last example, we created a parametric shelf generator where a fabricator can experiment with different shelf parameters like height, width, depth, shelf count, and spacing. Again, because Imprimer notebooks are live, changing anything causes the rendering to be updated immediately, as well as all the 2D geometries and cutting paths in real time. We also included testing functionality to test the fits of the joints, which can vary by machine. Taking a step back, having programming as a foundation is critical because it helps us work with a variety of domains. For example, deep learning, data visualization, and robotics. However, when it comes to manipulating physical matter, we don't yet have reusable code infrastructure that helps the community tackle new challenges that conventional tools haven't yet been designed for. In this light, Imprimer is a first step towards robust physical-digital programming, where challenges with tooling, materials, toolpath generation, and safety are all handled through code. In a future with robust physical-digital programming, practitioners from diverse backgrounds can confidently work with programmable machines in new ways and share their work with the community. That being said, we urge you to try Imprimer yourself. To browse the notebooks we authored for the examples we shared, head over to our collection on Observable notebooks. If you'd like to actually use the notebooks with your own Shopbot, you'll need to run additional code for the network architecture, and support for more machines is coming soon. Finally, we'd like to thank the Alfred P. Sloan Foundation for generous support in making this work possible, and to you, our audience, for listening.